All right, guys, welcome back. Good to see you. We're going to be talking about section 4.3. If you're looking ahead, you may notice that section 4.3 is the very last section in this chapter. That's a pretty important detail, as you can probably guess what's coming up next. If this is the last section, on Friday we'll be doing a comprehensive review, including any questions you guys have over any of the problems we've had so far, as well as on this weekend, the tests will be posted. The test will likely be in a Google document or a PDF of some kind. I haven't decided yet, but it will be posted this weekend and be due on Monday. So let's go ahead and get your homework up here. 4.3 is the section. It is on page 392 slash 347. Sorry, 329 slash 347. It is numbers 1 through 5, odds, as well as numbers 7 through 23, odds. You may notice this section is rather short in terms of the homework. That is because there's a technology portion of this one that we will be skipping for now, but we will eventually come back to that towards the end of the semester if we have time. That is because it's calculator based, and if I don't know what kind of calculators you guys have, it's kind of hard to do it. So we'll likely do that as either an interactive thing, or we may just post a little video about it some other time. So let's go ahead and talk about section 4.3, some of the big details you need to know to get you ready for your homework and to understand some of the textbook. So first thing to mention here, as you can see, the section is talking about fitting linear models to data. So we're sticking with the real world problems, we're sticking with the linear problems in particular. And so the first thing you talk about is something called a scatter plot. Now, scatter plots are by definition real life. You will never see a scatter plot in like a geometry problem that's, just talking about angles. You never see a scatter plot in a typical Algebra 1 or Algebra 2 problem, unless they're specifically based upon something realistic. Because scatter plots are determined from data. These are simply graphed points from a given set of data. Big detail there. These are points. Big word there. Meaning that they're going to show up as just a variety of different values. As you can see right here, we have this table here that showcases, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, looks like 15 different points. Notice that there's no line, there's no parabola, there's no weird curve. It's just a collection of points, individual values. And that's really important because when you're understanding scatter plots, you have to understand that they are not actually individual lines or anything. They're points that we're going to attempt to find meaning from. If you want to talk about your average use of mathematics, scatter plots is one of the biggest one. If you go into things like marketing, if you go into things like data analysis for a company, if you go into a company and plan on actually using mathematics, it's probably going to involve scatter plots and your attempts to understand them. So if you look at this data, a mathematician looks at this data and tries to get some information from it, tries to make some predictions. And one of these things is called a line of best fit. Now, a line of best fit is by definition a guess. It is an accurate guess, it is a logical guess, but it is a guess. It is meant to be a prediction of how you think this function is behaving. Specifically, do you think the function is increasing or going up? Do you think the function is decreasing or going down? Do you think it's constant? What information gives you that detail? If you look at this group of points, you might indicate that this is a constant relative over time, meaning there's not a huge trend upwards or downwards as we move from left to right. It seems to be there's definitely some variance up and down, but it's not like it's grouping and then shooting upwards. It's not like it's grouping and then shooting downwards. So in this case, for this particular problem, a line of best fit might be going directly across. Now, the point of a good line of best fit is it should hit a few points. However, this is not required. You cannot just be like, I'm going to choose this point and I'm going to choose that point and that's going to make my line. You have to use it based upon the general trend and ask yourself, does it make sense with what you're doing? You look at this picture, I look at this picture, and I think to myself, it doesn't look like there's a whole lot going up or down. So I wouldn't want to pick like this point and draw a line between them because it would look like it's trending downwards. Nor would I want to pick this bottom point here and this outer point here because it would look like as if it's trending upwards. The goal of a line of best fit is to accurately and clearly represent the given information. And we'll often call this a trend of the data. A trend indicates how it is changing over time. It's similar to a slope. So, a line of best fit is an indication of how the function is changing. It shows how it's, a positive or a negative, increasing or decreasing, but it's a prediction. You can use points if you are able to, but it is not required, and it should be as accurate and as clear a presentation of the trend as you physically can get. Again, if you don't believe it is going up over time, then you shouldn't put a line of best fit showing going up. If you do not believe there is one going down over time, then you should not show a line of best fit that is going down over time. Now, line of best fits are tricky because they are a prediction, a guess. If you put a line going across in this set of data, we can do a couple different ones. The goal should be to hit as much and as close as possible. So, as much and as close to as many points as possible. We want it to have as clear indication of what is closest. Now, for example, we're going to now move on to a graph that I'm going to make. So let's make a grid. It is common with these types of problems to stick primarily in the first quadrant. That's where everything is going to be dealing with positives. So let's look at our little grid. I'm going to put some dots here, showcasing kind of a trend of this function as it relates to time. And so in this case, I've got, somewhere between 20 and 30 points. And you can see, based on this scatter plot, which this is a scatter plot, that based on the information given, we are increasing over time. We are going up. As the x is going to the right, we are tending to go upwards. So this would say to me that the function is going to be increasing. So my line of best fit should showcase that fact as a line. Now, I'm going to do a couple different lines of best fit. Each one of these is decent, okay? It's important to note that each one of these attempts to get the same information across. So this first one, I would say, is kind of my bad option. It's just to kind of stick to the tops, okay? This is a bad best fit because while it does hit a bunch of these at the top, there's a bunch more that are also farther down below. And so we could make the same argument for one down below. I like to call these my upper and lower lines of best fit. They're not great. They kind of encapsulate all the data, but they don't really indicate anything for a lot of the points. Like if I'm using these two dots, yeah, it works for these two, but not for the rest of them. It's not a good guess in terms of where my next dot's going to be. Okay? I would say this red line is probably a really good line of best fit. And it's not perfect, by any sense. It's sort of in the middle of all of my data. It definitely showcases the trend, what's happening over time. It's definitely increasing. And if I asked you to predict something, this red line would be the best prediction. Sure, it's a little off for like dots like this dot or dots like this dot, but in general, it's close for as many as possible. Okay, this represents a good line of best fit. Now, anytime you talk about a line of best fit, you want to make sure to get down to just one. So that's great to showcase kind of like the good and the bad. Let's do a similar process for this one. Okay, we've got our data. You can see here we've got, 12 points, and we're supposed to find a line of best fit. Now, for this one, I want to pick one line, one singular line that I think is going to represent all of this data. And yeah, there's going to be some points that are going to be too far above. There's going to be some points that are going to be too far below. But I should get a good general trend for what this thing looks like. So for me, I'm going to try to choose this one. Is it perfect? By all means, not so. But it's pretty good. It's kind of in the middle of all of my data. Now, if I do this for my line of best fit, I can also determine the actual equation of the line of best fit. How do I do that? Well, the same process I used before. I can find a slope, and then use a point and the slope to determine point-slope form. So, provided that I can find the slope, I can use point-slope form by just picking a point and then finding the equation. Now, when I'm finding my line of best fit, some tricks to know. One, you choose the points. You choose the line, so you choose the points. It is best to use ones that are given that are either on or very near this line. So in my example, I might want to use this one, put a little star there, and maybe like this one, put a little star there. These would be two good points to use because they're both very close to my red line here. So these would be good points to help me find the slope. Because remember, I can find the slope as long as I have 2 points. This one would be an equally good one. I can also just choose one that isn't on the graph at all. Like I could come over here and be like, you know what? I really like this dot over here. Like this is an option. It works because it's on the line of best fit. When you choose your points, they do not have to be given points, as long as they're on the line. Now, it's best if they're given. That's why we typically want to choose a few points that are on the line to make this a little easier to choose which ones are right, but they don't have to be. So if you find yourself looking at this data going, is that, 0.3, 0.4? Don't, okay? Use the information you can. Maybe you can adjust your line of best fit a little bit to make it match your points better. Or maybe there's a point that is somewhere in between, like this one right here. This one might be a good one, right? It looks like it's a nice number. And so that might be a great one to pick for my line of best fit. Okay? Number 2. Just like how you choose the line and you can choose your points and they don't have to be given, when you plug into the form, make sure to check your work. If you can, graph this table. There are multiple things out there to teach you how to graph a table using a calculator. And in fact, if you just use like Excel or even Desmos can do a graphing of a table, if you just Google how, you can actually then graph the line of best fit and see if it actually matches your results. Because the worst thing you can do is to pick 2 points and try to plug in, make some kind of mistake, and then your line ends up shooting in the wrong direction. That's the worst thing that can happen in these cases. It's because then you got to restart. So make sure when you're doing these, you need to be able to find the slope and use the slope to find point slope form and rewrite it into standard form. You can choose the line, so you can also choose the points. So make sure to choose points that are easiest to work with. These do not have to be points that are given to you. So make sure to use points that are best available based upon what you chose as your line of best fit. And then always make sure to check your work for these. Now, a few general trends to note to remind ourselves. When you do the slope part of this, remember, positive slopes go up. Negative slopes go down. If you look at your picture and say, it looks like it's going down, but then you do your slope and you're like, why is my slope positive? You probably made a mistake. That's an easy thing to check. Because you're going to be dealing with a lot of data. You can easily look at the picture and be like, okay, I chose these 2 points. I know from the picture it looks like it's going down over time, so I better make sure my slope is going down as well. And you can even go farther and say things like, well, how quickly is it going down? Because if it's near zero, it's going to be near flat. And so if it's only just a little bit going down, you should have an answer that's really near zero. If it's going down really fast, then you should have an answer that's rather large and negative. So you can use this information to dictate what this thing will look like and how to get more from the data you have. Okay, so let's take a moment, pause right here, and review some of the things we've talked about so far. This is a big part of our notes, and let's make sure we're all on the same page before we go forward. First thing to mention, so far we've talked about line of best fit. These are pieces or components that indicate how the function is changing over time using a scatter plot. So these are not given lines or given equations. We are given points, and we have to determine, based upon our intuition, a guess or a prediction. How do we think this function is changing? Does it look like it's going up? Does it look like it's going down? Does it look like it's remaining flat? Okay? When possible, we should use a few of the points to help us with this, but it is not required as long as it fits within the trend, how much it looks like it's going up or down. Now, you want to make sure that it fits relatively in the middle of your data. If you have it too far up or too far down, that's considered bad. These are still trend lines, but they're bad trend lines. Like, I could have a trend line in this picture that is just going like this. And you look at that and be like, yeah, it's a trend line, but it's bad because it ain't doing what it's supposed to be doing. So use the information you have to help you out here. Once you've got your trend line in place, you can find an equation just like you find an equation with anything. You need 2 points. Remember, you choose the line, so you choose the points. They do not have to be given points. So you can use either ones that match directly on the line that were part of what was given to you, or ones that are, on the line but not given. So like these two. And then finally, make sure to check your results. Use some intuition. If you know you have a slope that's supposed to be going down and therefore it's supposed to be negative, make sure when you plug it in, you get a negative answer. If you know you have a slope that's supposed to be going up over time, because the picture is going up over time, then make sure the answer is positive. Make sure it makes sense. I cannot say that enough. With these kinds of problems, they should make sense based upon what you see, as long as you understand the pieces that are going into it. All right. Next thing to talk about is some definitions. So let's pull them up. All these definitions fit with how a model acts, and they're pretty common in industry as well. So, model breakdown. It's going to be our first definition. Interpolation. And extrapolation. Are my next two. Now, you'll hear these pronounced a few different ways depending on who you talk to. If you talk to more British people, these are interpolation and extrapolation. If you talk to more American people, this is extrapolation and interpolation. It just kind of depends on who you talk to. And model breakdown is just model breakdown. I always think model breakdown is, what happens whenever they turn 30. But, that's what happened to my car anyways. Let's take a look. Model breakdown. When you're looking at something that is realistic, everything that's realistic has a limit of how useful it is. If you're looking at something like stock prices, it's going to be a scatter plot. If I'm looking at something like the stock price for something like Walmart, as you go through the day, it tends to go upwards. Some days it tends to go downwards. Like, it has some trends, some things that it's doing over time. Now, model breakdown is, let's say this is, stock price over 2 years. So you can see how it makes kind of like this nice little curve here. Well, here's the thing. Over these 2 years, this is going to be an accurate representation. You can see it's going to get, some accurate answers. We can come up with some lines of best fit for different parts of it. Like, we could split this information in half and do a line of best fit for this side, a line of best fit for this side, and get some real useful, accurate information. But let's say I want to look 20 years in the future. This isn't realistic based upon what we know in the data. We only have data over the course of 2 years. Maybe 5 years down the road, the stock price has jumped way, way up, so it's off the page up here. Or maybe the company crashed and it's down to zero. We don't know. There's a certain limit to how useful your data is. If you, many of you guys were very young, but if you grew up in the 2008 stock crisis, when they had the housing market collapse, everybody looked at the data and said it's going up and over, going up, and everybody predicted that it would keep going up for years. The problem was they had a model breakdown where they had unrealistic expectations of how useful their data was, because the housing market hit a spot where suddenly it started to crash. And so all the data they had used was basically useless. We hit a point in every realistic scenario about how useful our data actually is. If you look at something like the price of gasoline, you notice that if you go out and drive right now, I encourage you guys to stay home, of course, but if you're going out and driving, the gas price has dropped significantly. If you record the gas prices over the last couple weeks, so gas price, it started off, a few weeks ago, it was in the $2 range. And, now it's sitting, in some places at like, the $1.19 range, which is really cool. And so, there's, data showcasing how this thing is going down over time. But here's the thing, this is over the course of, 3 weeks. That's how much time it's taking for this gas price to drop. But if we look at this and say, oh, look, line of best fit, or a better line of best fit perhaps would be, down to here or something. If we get a line of best fit out of this data, well, eventually this data is not going to be very useful because it's going down over time. You're eventually saying, hey, at some point in time, we're going to end up down here in the negatives. And that makes no sense. Like, we can't have negative gas prices. It's not going to be, offering you money to take the gas off their hands. That's not realistic, okay? It doesn't make sense with the limits of the data. And so there's always a breakdown in any model of how far it can go before it stops being useful. And with all data, that is dependent upon what you know. You just can't get any more information. I like this example they have in the text where it talks about the chirps of crickets. I think that's interesting because it showcases this temperature and gives you some data from that. And here's the data for the temperature. That's cool, right? But what if you just, kept going up in temperature? What if you hit like 200 degrees? At some point, these crickets going to die, right? They're going to get burnt to a crisp in the Sahara Desert or something. They are going to stop chirping because they're going to be dead. So even though it looks like over time this graph is going up, there's going to be a point where it's just not useful. The data has a model breakdown. Okay. Interpolation and extrapolation. Interpolation means to guess within the given data values. Whereas extrapolation means to guess outside the given data values. This one, I'm going to use a picture in the text. It's actually this one right here. If I asked you about interpolation, let me make a very, very rough copy of this graph here. So it looks like we have, 10, 20, 30, 40, and eventually 50 right up here. And then we got, starting at 40, 50, 60, 70, 80. And let's grab some points here. We have the point 44 chirps at 80 degrees, so 40, so that'll be 10, 20, 30, 40. So we got 44 at 80, so that's a dot right there. We got 35 at 70.5. I'm using the information from the above table right here. Let's see, we got 20.4 at 57, so 20.4 at around 57, so right about there. 33 at 66, so 33, 66, right about there. We got 31 at 68, so 31, 68, right about there. We have 35, 72, so 35, 72. Ooh, that's pretty close together. We have 18.5 and 52, so 18.5 and 52. And then we have 37 at 73.5, so 37, 73.5. And then 26 at 53, so 26 at 53. Let's go right there. This is an okay representation of what this thing looks like, right? Even looks pretty dang close, man. I'm so good at this. All right. If we were to ask to put in the line of best fit, we'd want something that's kind of in between here. Like, say, like this. And this would be our line of best fit. So we might be able to use things like this dot and maybe this dot to determine the slope. But let's talk about interpolation and extrapolation. Interpolation would be trying to answer the question at, okay, guess the value when x equals 28. So if you look in our list of data, 28 isn't in our chirps, right? And so if we ask to guess what's happened at 28, 28 is right here. And so we can make a guess that the answer is going to be somewhere in here. Now, interpolation is always in between your set of data. So in terms of the picture, anything in this box would be considered interpolation. Okay? Anything inside is interpolation. Or interpolation, depending on who you ask. Because we're guessing within the boundaries of the data. So this is your guess. Your guess has to be, let's see if I can write this. Your guess is between the lowest and highest given values. Okay, so how does this compare to extrapolation? An extrapolation question would be very similar, but an extrapolation question might ask, okay, guess the value when x equals 15. Okay, but you notice again, 15 is not on my given information. Right? The lowest value we have in our given information is 18.5, and so 15 is outside of that group. So these are considered to be extrapolations because they're outside of the group. Now, by definition, interpolations are always more accurate. That does not mean they are always right. It is possible that you make a guess using your line of best fit, and that guess is way off. Right? Our line of best fit isn't perfect. There are some values above, there are some values below. But it's always going to be more accurate, okay? More accurate. Whereas this one will always be less. It's a consequence of having the data versus not having the data, right? Because if I go over here and I'm like, okay, what happens when we have, instead of 40, 44 is our biggest number? Yeah, let's go 44. What if we went to like 50? Maybe 50 is impossible. Maybe at 50, the animal dies. Like, there's just no information out here in this vast void of unknowledge. Because maybe, as this thing is going along, the farther we go, maybe it's supposed to be, like, down here. So our line of best fit is actually terrible. Like, without more data, extrapolation is always harder and always less accurate. Okay? Whereas interpolation is decent. It's a good guess, okay? Not perfect, but a good guess. It is always going to be more accurate to use interpolation versus extrapolation. There we go. So this is my data pulled directly from the table. This table is on page 323, explaining each one of these. And notice my definitions again. Model breakdown. It's a realistic limit of how useful your table is going to be. So in any given realistic scenario, it is more or less likely that that function is going to stop working. So where does that function happen? And it may be near the edge or maybe really far away. We don't always know, but eventually the model always breaks down. Okay, last bit. I'm going to skip some stuff on here, mainly because we've talked a lot about it. This is a great example of interpolation versus extrapolation. Take a look at it. Okay, if we ask you to guess any x value within this little boundary here, your answer is going to be somewhere in here, and it's considered interpolation because it's between the lowest and highest values of my function, between the lowest x and the highest x. Extrapolation is anything outside of that. So if I ask what happens at 10, our line of best fit is out here, but how accurate is that? That's extrapolation. It's where our x values are outside of the boundaries. All right, last piece for us, you can see how they do a lot of technology things, is called the correlation coefficient. Okay, last piece for the chapter. Correlation coefficient. If you've ever seen any news articles or watch the news or read any kind of information about data, they often talk about this term called correlation. Now, in a lot of news, they'll talk about a strong versus weak. However, in math, this is terrible because strong means different things to different people. And so in math, we don't really talk about strong versus weak. First, let's go ahead and define correlation coefficient. There's a definition here in the text. I like my definition. Correlation coefficient is how tight your data is to the line of best fit. How tight would the data be? If you look at these examples, you can see that the positive 1 right here, the data is real tight. There's hardly anything, like anybody could connect these dots and make a line. And we could all pretty much get the same line. So we have a range of values between -1 and +1. At -1, this is considered to be strong negative correlation. At +1, this is considered to be strong positive correlation. Strong means that it's easy to connect the dots. So if we look at our first picture here, on number 1, this right here is considered a strong positive correlation because it is definitely positive because it is going up over time. It's strong because we can all agree that this is how you would connect these dots. Okay? Same thing over here. This is a strong weak or strong negative correlation. It is definitely negative because it's going down over time. But if I gave all of you a ruler and said draw a line using these dots, everybody should get the same line, give or take a very tiny amount. Now, so the question is, what happens in between? Well, at 0, this is considered to be weak. Weak means it's impossible to draw a line, and we all agree what that line is. On the bottom row here are some great examples of weak, but I actually like this top example here. This top example is a very common one. So, for example, this top one, you notice that it just looks like a blob. If I asked you to draw a line through this blob and said, make sure it's a line where you get the best guess, some people would look at this and be like, I can see some dark in here, so I'm going to draw a line that kind of goes up over time. Some people are like, I can see some dark going this way, so I'm going to draw a line going down over time. And some people are like, I can't do anything, so I'm going to draw a line across. And some of you, the really smart ones, will look at this and go, yeah, I can't draw a line. If you cannot guess If you have no idea where the line of best fit is, like, not like, oh, it could be, like, no idea. If you can't even get close to coming up 1, then the correlation coefficient is probably a 0. Now, if anyone could do it, then it means it's strong, either positive or negative. Let me put it to you a different way. If I could hand the pencil to my 5-year-old little niece and she could connect those dots without any trouble, it's probably strong, either positive or negative. How do we know whether positive? Strong positive always goes up over time because it's positive. Positive goes up. And strong negative always goes down over time. So when you look at a picture, you have to ask yourself, is it a tight fit going up? Is it a tight fit going down? The tighter the fit, the closer your number is going to be to 1. So you can see right here how this is an example of a 0.8. So you can all see that it's going up over time, but it's definitely spread out a lot more than the 1. So you notice how it's close to 1? 0.8 is pretty close to 1, but it's definitely not a 1. Okay, 1, we should all be able to get the exact same. Like some of you guys might be able to do one that's kind of more flat. Some would do one that's more steep. Like it's hard to get a line of best fit that everybody can agree on. A 0.4, like you can see how it's just barely got any indication it's going up. Like, yeah, there's a little bit more at the bottom than there is at the top. So yeah, it's a little bit increasing. But it ain't much. Like this could be even like a 0.2. Like it's barely increasing at all. This middle one here, nothing. You would spend hours trying to convince me that there's any reasonable line that you could draw on here that represents this data. And you can see the negative 0.4, negative 0.8. Again, it looks like it's just going a little bit down. Now it's much more clearly going down. Now it is definitely going down over time. And you can see that no matter how much or how little it's going up, or how much or how little it's going down, if it's tight, it's a 1. So if it's tight, 1, 1, 1. Yes, this is strong positive, strong positive, strong positive for all 3 of these. And this one, it has an undefined correlation coefficient. Because if I put a 0 would indicate that it's a blob. This ain't a blob. But you notice that this one's a 1, this one's a 1, this one's a 1, this one's a blank. Because it isn't a positive or a negative, it's nothing. Negative 1, negative 1, negative 1. And all 7 of these are examples of no correlation. You got a wave here, you got a box, you got another box over here, a diamond. You got what looks like Pac-Man trying to devour this 0 up here. You got some gang symbol that we got a new crypt group going. You got what looks like a donut. And then you got the block of dice. Like there's no line that's going to represent this data well. So these are the correlation coefficients. And you need to be able to graph the data and ask yourself, how reasonable is the data to being a 1? You know, when I look at this set of data, is it a strong or is it weak? You know, is it going up? Is it going down? If I go back to this list, here's some previous examples. I would say this one has a correlation coefficient of, well, let's say negative 0.9. It's pretty tight. Like it's decent. Maybe even like a 0.8 if we want it to be safe. But it is clearly going down. That's why it has to be negative. Okay, and it's decently tight, so it's close to negative 1, but definitely not negative 1. If you look at this part of the data, you could probably easily convince me that this part would be positive because it is going up over time, but it's very loose. It's going back and forth quite a bit. And so for this half of the data, let me split this into 2 pieces. For this half of the data, you might say this has a coefficient for correlation of, say, like 0.4. Yeah, it's definitely going up, but it's very loose. Whereas on the other side, this is much more tight, but it's also going down. Like, it's much easier to see in this one that it is going down than it is in the other one. And so you might say this is a correlation coefficient of something like negative 0.6, you know, maybe even like 0.7 or 0.8. And you can get fancy with these because this is very interpretive, but we would all get near the same answer. There's no one right answer for a lot of correlation coefficients. It's just, unless it's a 1 or a 0. Those are the only times where it's really, there should be one clear answer and there's no real arguing the point. Okay? But otherwise, there is some argumentation that can be had, and there's more than one way to put a right answer. If we look at these other examples, this is clearly going to have a positive, but, it's pretty loose data, maybe like a positive 0.7. This one's pretty negative. I'd also give it probably like a negative 0.7 for its coefficient. Like, it's pretty spaced out. Like, it's easy to see it is going down, but even still, it's not very tight. It's not a tight packing. And so this one right here is a big detail that for some problems, all they ask you is to determine the correlation coefficient and defend your answer. So make sure when you look at a picture, you can say, is it clearly positive? Is it clearly negative? Is it tight, therefore a 1, or is it not so tight and therefore a decimal of some kind? Or is it nothing at all, in which case it's a 0. The more data you have, the easier this is to do. So make sure you're plotting all of your data points that are given and use the information you have. That will be about it for today. Reminder that we will be skipping some of the technology portion that's in this section, so there's a lot of pieces in here that we'll be going through at a different time if we have available. On Friday, I will be answering any questions. If you have any questions, please either send them to me via email, shoot them to me on the Google Classroom, add a comment. If you have any questions over any of the homework problems, I will be answering any and all of them on Friday. So get them to me before Friday at noon. I will post Friday at noon's video after I get as many questions as I can done. On Friday, you'll have a review assignment. It is, of course, optional because all review assignments for me are optional. And once that assignment is done on Saturday, during the day at some point, I will post the exam. The exam will be 100% take-home, obviously, and it will be due on Monday. Make sure it gets into me before your stuff is finished. That will be finished for today. Don't forget, page 329/347 from section 4.3, 1 through 5. This is not right. This should be 1 through 5 all, and 7 through 23 odds. Okay? That'll be it. Hope you guys enjoy the rest of your Wednesday, and I'll see you guys on Friday.